Welcome to iLecture Online, and here's another example of how you do problems using Coulomb's law. In this case, I'm going to show you an example where all the charges are on a single line, but here instead of two charges, there are three charges. So let's go ahead and read the problem. It says we have a 6 microcoulomb charge that is placed at the origin, and a 4 microcoulomb charge, it's a negative 4 microcoulomb charge that's placed 2 meters to the right. And then there is a third minus 8 microcoulomb charge that is placed on the x-axis 2 meters to the left of the first charge. What is the force on the second charge due to the presence of the other two? All right, to figure out how to do this problem, you want to put a nice little diagram together. So let's do that. So here's our x-axis, and here's our y-axis. And we don't need much of a y-axis because all the charges are placed on the x-axis. The first charge, right here at the origin, is a positive charge, so we indicate as a positive charge. Call this one Q1. We have a second charge that is placed 2 meters to the right, so let's put it right here. That's a negative charge, and we'll call this one Q2. And then there's a third charge that's placed to the left, the same distance to the left as the Q2 is placed to the right. So put it right here, and it's also a negative charge, and this is Q3. So indicate that this here is 2 meters, and this distance right here is also 2 meters. All right, so that's what our picture looks like. Now, where do we start? And I always recommend that the first thing you do is draw vectors representing the forces acting on the charge in question here. So we're trying to figure out what the total net force is on this charge due to the presence of these other two charges. So always start with drawing some vectors. All right, so we have Q2 here, we have Q1 there. Q1 is positive, Q2 is negative, so they attract each other, which means that the force on Q2 to the presence of Q1 is to the left. So we have a force in this direction. So this is F12, which indicates the force between Q1 and Q2. So it's always good to use some good subscripts to indicate what forces we're dealing with. All right, now we're going to consider these two forces. What is the force on Q2 due to the presence of Q3? Now these two charges are negative, so they oppose each other or they repel each other. So the force on Q2 to the presence of this one should be to the left. So this will be F between 2 and 3 to the right. Now I drew this arrow a little bit shorter than this one because the distance is twice as far, and knowing Coulomb's law, the force is proportional to the inverse of the distance squared. So if it's a shorter distance, it should be smaller force, even though the size of this charge is bigger. This is an 8 microcoulomb charge, as this is only a 6 microcoulomb charge. So let me write down the values of these to make it a little bit easier. So this is a minus 8.0 microcoulomb charge. This is a positive 6.0 microcoulomb charge, and this here is a negative 0.4 microcoulomb charge. All right, so that's probably what it should look like. And now we need to sum those two forces up to find the net force on Q2. Realizing that this is all on a single line, so when you do a vector sum, you can see that since this is presumably bigger than this force, that the net force is probably, and this pen doesn't work anymore, so we'll get rid of that one. Let's see if this one works. There we go, yes. So this will be F total, which is going to be a sum of F12 plus, I should say equal, and F23. You might say, well, wait a minute, why didn't I make this a negative? Well, it's indeed, when I equate what this is equal to, this will become a negative quantity, but right now I'm simply representing this as the sum of the two vectors, and so we just simply use positive values there. All right, let's go ahead and continue. What's the next step? So first, you draw a diagram, then you draw the vectors, then you realize that when you sum them up, this is a vector sum. But then how do you do a vector sum of vectors? Well, to do that, you find the magnitude of each vector first. So you want to find the magnitude of F12, and that will be equal to, using Coulomb's law, that will be equal to K times Q1, Q2 divided by the distance between them squared. Now notice how I indicate the distance between them squared. I use the subscripts 1 and 2 to indicate that's the distance between Q1 and Q2. I'm only going to use positive values because I'm finding the magnitude of that vector. So So this is equal to 9 times 10 to the 9 newtons meters squared per Coulomb squared, times Q1. Q1 right here is 6 times 10 to the minus 6 coulombs. Then we have Q2. Q2 is over here, so that's equal to 4 times 10. Ooh, did I say 0.4? That's not what I meant to say. I meant to say 4.0. So 4 times 10 to the minus 6 coulombs. Again, I only use positive values because I'm finding the magnitude of that force, not the direction, and I divide that by the distance between them squared. So 2 meter quantity squared. And now we grab our calculator to find out what that is. So we have 9 e to the 9th times 6 exponent 6 minus, all right, times 4 exponent 6 minus equals, and divide the whole thing by 2 squared, which is 4. And so the answer here is 0.054 newtons. Again, the meter squared cancels out with the meter squared, the Coulomb squared cancels out with the Coulomb squared, and we're just simply left with newtons, which is good because we're looking for a force. All right, we now have the magnitude of the first force. Find the magnitude of the second force. So F between 2 and 3 is equal to K times Q2, Q3 divided by the distance between those two squared. Right? Plugging in the numbers. So we get 9 times 10 to the 9th newtons meters squared per Coulomb squared times the first, Q2 is 4 times 10 to the minus 6 coulombs. Then Q3 is over here, which is 8 times 10 to the minus 6 coulombs. Again, I don't care about the signs. I only care about the magnitude. Magnitudes are always positive. Divided by the distance between them squared. So that would be, what's the distance here? Well, we have 2 meters, and 2 meters, that's a total of 4 meters, and we have to square that. So let's see what that is equal to. So I have 9 e to the 9th times 4 exponent 6 minus times 8 exponent 6 minus equals, and then divide the whole thing by 16, and that's 0.018 newtons. 0.018 newtons. So now we have the magnitudes of both forces. Now we need to add those magnitudes together. Now again, since they're vectors, we can only add the x components and the y components together separately, but since there's no y components, we only have to add the x components here. So we have F total is now going to be equal to the sum of F1 and 2. So that's the force between 1 and 2, and the force between 2 and 3. So that's equal to. Now we have to be careful of the directions. Now that we're actually going to find the vectors, because remember, F12 is equal to the magnitude, 0.054 newtons, times the direction. And since F12 is pointed to the left, we make that a negative x direction. So this is the unit vector in the x direction, and we have to indicate that the direction is negative. And for F23, here we can see that it's directed to the right, so it's a positive 0.018 newtons in the x direction. So remember that we want to now make sure that we indicate the direction if now we're going to replace what those vectors are equal to. So this becomes minus 0.054 newtons in the x direction plus 0.018 newtons in the x direction. And so the total is now going to be equal to, add those two together, minus 0.036 newtons in the x direction. And here's our answer in vector format. That is the resultant force on Q2 to the presence of the other two. Magnitude, 0.036 newtons. Direction, along the negative x-axis, or in the direction of the negative x-axis. All right. That's how you do these types of problems. Okay.